Alright, so this time we're going to take a look at a pretty easy force problem, all things considered. Let me see if I can find chalk that doesn't want to scream at me. Alright, this time we're going to take a look at something that might be a little familiar. It may not seem familiar starting off, but we will talk about it. And at the end, after we've figured everything out, see how it connects to real life. So, I'm going to start off taking a look at a spring. And this spring has a natural length of 1.0 meters. Okay? So, when I just hang it there and nothing's happening, it stretches out. It wants to be at about 1.0 meters. I decide that I'm going to take a mass, some unknown mass equals question mark, and I'm going to hang it on this spring. And when I do that, the spring stretches out 1.1 meters. So it goes down 10 centimeters. Alright, I've got a drawing of what's going on. It stays there at about 10 centimeters lower than the natural length, at 1.1 meters, full extension, and it just kind of hangs there. We've seen applying a mass onto a spring in class. So, what I'm going to do is I'm going to declare a coordinate system. I'm going to come over here and say up is my plus y, just to be different, because we never see that. And I'm going to say y equals 0 is right up here at the top of the spring, so that I can keep track of my locations pretty well. So down here, this is a y equal to negative 1.0 meters. Let me write that a bit bigger. Y equals negative 1.0 meters. And then over here we've got y equals negative 1.1 meters. Okay? Well, I've got a mass. It's hanging on a thing, a spring, if you will. And I want to find out how massive that mass is. So I want to know how much heft it has, how much material is there. Okay, well, to find out that sort of thing, I'm probably going to be dealing with forces. We didn't talk about springs until we got to forces, so there's a good bet that this is related to forces. So if I think that forces are part of my solution, the next thing I want to do is I'll draw a free body diagram. And so this is a free body diagram of my mass. Well, this is near the surface of the Earth. So I expect that it has gravity pulling down on it. And it's just kind of sitting here. So we know that the spring is supplying a force upward. That's what's holding it up. I've hooked it onto the spring and let go of it. The spring sunk down a little bit, but then it's just holding the mass there. Okay. So I've got my free body diagram. Are there any other forces that I'm overlooking? No? None that I can think of. So this looks like it. Now I need to be able to do something with those forces. Wasn't there some sort of law dealing with motion and forces? Some sort of second law of some kind? Newton's second law. Newton's second law says the sum of forces equals the mass times the acceleration. Well, all of our forces happen to be in the y direction this time. That simplifies things. So we're going to do sum of forces in the y equals our mass times our acceleration in the y. And our sum of forces in the y, adding up all the forces that exist in the y, I've got a positive force of the spring. And I've got a negative force of gravity, so minus mg. Okay? Well, because both of these things are equal to our sum of forces in the y, I can set these guys equal to one another. So if I draw that back over here, I've got my force of the spring minus mg equals my mass times my acceleration in the y. Hopefully I'm not going out of the frame here, but I think I have a little bit of room. Alright, well that's pretty good. I've got the mass showing up in there a couple of times. That's what I want to solve for. Good, because I want that in my equation. G, that's my gravitational acceleration. When we're dealing with forces with little g, we always put it in as a positive. positive 9.81 meters per second squared, because we took care of our negative, our direction, here. Okay, so we don't want to double count the negative. All right, the mass is over here. Our acceleration in the y direction, we don't know that, but we hung the mass on there, it sank down over here, and then it just kind of stayed there. So if it's not accelerating up or down, speeding up, going down, or up, or anything like that, then we know that our acceleration in the y direction equals 0 meters per second squared. Okay, well that'll take care of that. I still have my mass over here times gravity. I don't know my force of the spring. Okay, so let's take a look there. If we check our equations, the equations that I gave you related to forces, we know that the force of a spring is equal to negative k delta x, or negative kx. Okay, that's Hooke's law. Well, do I know my k? Well, let me check my notes. I think I forgot to give a k. I apologize about that. Our k is equal to 196 newtons per meter. I looked it up in a table and found out that this particular spring has that k, that spring constant. It describes how stiff the spring is. Okay, so we've got that number. What about our delta x? Delta x was a displacement. Okay, well, I started off, in this case I'm dealing with the y, so I'm going to say that this is actually negative k delta y. Delta, what does that mean again? It means change, but specifically it means final minus initial. Well, here's my final situation, right? I have negative 1.1 meters is my y final. And my y initial is over here at negative 1.0 meters. So if I plug that in, I have my force of the spring equals negative my spring constant, which is 196 newtons per meter, times delta y, which is my final, negative 1.1 meters, minus a negative 1.0 meters. Well, the negative multiplies on the negative and they cancel each other out, so subtracting a negative is the same thing as adding that value. And I end up with my force of my spring equals negative 196 newtons per meter times, well, negative 1.1 plus 1 is negative 0.1 meters. Okay, well that negative cancels out the other negative here. Cool. And we end up with 196 times 0.1, the force of our spring, bringing it over here, where I can see it. Force of spring equals, what's that going to be? 19.6 newtons. Newton per meter times a meter gives me newtons left. Okay, well now I know my force of my spring. I can plug it in up here. I've got force of spring minus mg equals mass times my acceleration in the y. Sorry, I'm writing kind of small. My chalk is breaking, or not breaking, but disappearing quickly, so I had some problems with the big chalk trying to scream, so hopefully this will go all right. We know our force of the spring. It is 19.6 newtons minus our mass, which we're looking for, times 9.81 meters per second squared, and I realize I'm probably going off the frame. I'm going to set that equal to my mass times my acceleration in the y, but my acceleration in the y is equal to 0, so this whole thing is going to go to 0, right? So I end up with 19.6 minus my mass times 9.81 meters per second squared. I'm going to try and use this room here. So I'm going to add my mass times 9.81 meters per second squared to both sides. I end up with, down here, 19.6 newtons equals my mass times 9.81 meters per second squared. I divide both sides by 9.81 meters per second squared. Okay. and I end up with 19.6 divided by 9.81 meters per second squared comes up to just about 2 kilograms, and that's equal to my mass. So, I found out that my mass equaled 19.6 newtons divided by 9.81 meters per second squared, and that gave me that my mass was equal to 2 kilograms. Let me double check that. Yes. Okay, so we figured it out by applying Newton's second law on our free body diagram, drawing everything out, going in order. We drew things out. We labeled our coordinate axes so we could keep track of everything. We drew our free body diagram so we could see the forces that are going on, and then we applied Newton's second law on our free body diagram so we could add up our forces and relate that to the motion. In this case, it's not moving, so our motion, our acceleration in the y, ends up being 0 meters per second squared. It's not speeding up or slowing down. And so, carrying through, we found that the force of the spring was equal and opposite to the force of gravity. And we found our force of the spring using Hooke's law over here, the amount that the spring stretched out, and our spring constant that describes our stiffness of our spring. And then we finally were able to solve for our mass of 2 kilograms. So, this is something that you probably encountered on a regular basis. These are called spring scales. It's exactly this sort of thing that when you go to the supermarket and you've got one of the little pan things that you put a bag of apples in, and the little lever goes to a specific point that tells you how heavy it is. Well, that's what it's doing. The heavier something is, the more it drags this down, and they've just got the whole thing set up where the lever will go up based on how much it's stretched, and how much it's stretched is directly related to the total force. And if it's equal and opposite, we can tell how much something weighs, what its mass is. Well, those are two different things, but what its mass is, or in the case of what we're often looking for, its weight in that case. Near the surface of the Earth, they're pretty similar. We can determine that just by seeing how much the spring elongates, how much it stretches out. And so when you actually put your hands on those spring scales, or on the scales at supermarkets, you can kind of feel the same thing as pulling on a spring. Well, that's because they've actually got springs inside of them. That's how the whole mechanism works. Okay, so